Picture yourself standing on a mountaintop on the clearest night of your life. You raise a pair of binoculars to your eyes, and suddenly the universe explodes into view. Stars that were invisible moments before now shimmer like diamonds scattered across black velvet. You adjust the focus, and more stars appear. Then you wonder, if I had the most powerful telescope ever built, how far could I actually see? What lies at the very edge of our cosmic vision? This isn't just idle curiosity. When we ask how far we can see in the universe, we're really asking one of the most profound questions in all of science. What are the ultimate limits of human knowledge? How far back in time can we peer? And what does it mean that there might be places in the cosmos that we can never, ever see? Tonight, we're going to embark on a journey to the very edge of the observable universe. We'll discover why seeing farther into space means looking deeper into time. We'll explore how the universe itself sets boundaries on what we can observe, and we'll uncover the mind-bending reality that the farthest thing we can see isn't a star or a galaxy, but the afterglow of creation itself. You might think this is simply about building bigger telescopes, but you'd be wrong. The limits of cosmic vision are written into the very fabric of space-time, encoded in the expansion of the universe, and hidden behind a wall of light that marks the moment when the cosmos first became transparent. Beyond that wall lies a realm we can glimpse only through gravitational waves and the faint whispers of particles that barely interact with matter. As we stand here with our imaginary binoculars, we're about to discover that the universe has been playing a cosmic shell game with us for nearly 14 billion years. The question isn't just how far we can see, but whether we're prepared for what we might find lurking at the very limits of perception. Some of those answers will challenge everything you think you know about space, time, and the nature of reality itself. So, put down those binoculars for now. We're going to need something far more powerful for this journey. We're going to need the combined might of human ingenuity, the most sophisticated telescopes ever conceived, and, perhaps most importantly, we're going to need to completely reimagine what it means to see in a universe that's far stranger and more wonderful than our mountaintop view could ever suggest. Are you ready to peer into the cosmic abyss and discover just how far the human eye can reach when we give it the tools to touch the very beginning of time? Let's find out what happens when we point our most powerful instruments not just across space, but backward through the entire history of existence itself. When we talk about seeing far into the universe, we need to begin with a fundamental truth that would have astounded astronomers just a century ago. Looking out into space is the same as looking back in time. This isn't metaphorical poetry. It's the literal, inescapable consequence of the finite speed of light. Imagine you're sitting around a campfire with friends on a summer evening. When you look at your friend sitting across from you, you're seeing them as they were a few billionths of a second ago, because that's how long it took light to travel from their face to your eyes. It's an imperceptibly small delay, but it's real. Now scale that up. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The sun appears to you as it was 8 minutes and 20 seconds in the past. And when you gaze up at Proxima Centauri, the nearest star beyond our solar system, you're looking 4.2 years into the past. This relationship between distance and time is what makes astronomy the ultimate time machine. The farther we look, the further back we see. And here's where things get interesting. If the universe has a finite age, then there must be a limit to how far back in time we can look, which means there's a limit to how far we can see. But determining that limit isn't as simple as you might think. The story begins in the 1920s with a lawyer-turned-astronomer named Edwin Hubble, working at Mount Wilson Observatory above Los Angeles. Hubble made a discovery that literally expanded our understanding of the cosmos. He found that distant galaxies weren't just sitting there in space. They were racing away from us. More shocking still, the farther away a galaxy was, the faster it was receding. This observation led to one of the most profound realizations in human history. The universe is expanding. Space itself is stretching, carrying galaxies apart like raisins in a rising loaf of bread. This expansion means that when we calculate distances to far-off objects, we have to account for the fact that space has been growing throughout the entire time light has been traveling to reach us. Picture a cosmic postal service where letters take billions of years to deliver. When a galaxy sends us its light, the universe might be 10 billion light-years across. But by the time that light reaches us, the universe has expanded. And that same galaxy is now 15 billion light-years away. The light still took 10 billion years to reach us, but the source is now much farther than 10 billion light-years distant. This is why cosmologists distinguish between different types of distance measurements. There's the light travel distance, which tells us how long ago we're seeing an object. There's the proper distance, which tells us how far away that object is right now. And there's the co-moving distance, which factors out the expansion and tells us where that object would be in a non-expanding universe. The current best estimate for the age of the universe is 13.88 billion years. You might think this means we can see objects whose light has been traveling for 13.8 billion years, and you'd be absolutely right. But here's the kicker. Those objects are now much farther away than 13.8 billion light-years due to the expansion of space during the light travel time. The most distant object we can theoretically observe emitted its light when the universe was just beginning to become transparent, about 380,000 years after the Big Bang. At that time, this region of space was only about 42 million light-years away from where our Milky Way would eventually form. But today, due to cosmic expansion, that same region is approximately 46.5 billion light-years away. This distance defines what we call the observable universe, or the cosmic horizon. Think of it this way. Imagine you're in a vast, dark theater, and someone starts turning on lights one by one, beginning at the center and working outward. The observable universe is like the expanding sphere of illumination around you. At any given moment, you can only see as far as the light has had time to travel. But that sphere keeps growing as time passes, and light from more distant regions finally reaches you. But the cosmic horizon isn't a physical wall or barrier. It's more like the horizon you see when looking out over the ocean. As you move, your horizon moves with you. Similarly, as time passes, our cosmic horizon expands, and we can see objects that were previously beyond our reach. Every day, light from objects that are now about 14 million miles farther away crosses into our observable sphere. Here's where the story takes a fascinating turn. In the early universe, Space was filled with a hot, dense plasma of protons, electrons, and photons. This plasma was opaque to light, like trying to see through a thick fog. Photons couldn't travel far before bumping into particles and scattering in different directions. The universe was effectively blind to itself, but as the universe expanded, it cooled. About 380,000 years after the Big Bang, something remarkable happened. The temperature dropped enough for electrons and protons to combine into neutral hydrogen, atoms. Suddenly, the cosmic fog lifted. Photons could travel freely through space for the first time. This moment, called recombination, represents the farthest back in time we can see using ordinary light. The light from this cosmic dawn is still reaching us today, stretched by billions of years of cosmic expansion from visible light into microwaves. We call this the cosmic microwave background radiation, or CMB. It's the afterglow of creation itself, a baby picture of the universe taken when it was just 380,000 years old. This creates what cosmologists call the surface of last scattering. It's not a physical surface, but rather the moment when the universe became transparent. Before this time, the universe was opaque, and we cannot see farther back using electromagnetic radiation of any kind. The CMB represents our absolute limit for optical astronomy. But here's something that will bend your mind. The regions of space that emitted the CMB light we see today are now so far away that they're receding from us faster than the speed of light. How is this possible without violating Einstein's special relativity? The answer is that while nothing can move through space faster than light, space itself can expand at any rate. These distant regions aren't moving through space away from us. Space is stretching between us and them. This expansion creates what cosmologists call the particle horizon and the event horizon. The particle horizon represents the farthest distance from which light could have traveled to reach us since the beginning of time. It defines the boundary of the observable universe. The event horizon, on the other hand, represents the farthest distance from which light emitted today could ever reach us in the future, given the accelerating expansion of space. Recent measurements suggest that the observable universe has a diameter of approximately 93 billion light-years. But remember, this doesn't mean the universe itself is only 90 billion light-years across. The universe might be infinite in size, or it might be much larger than what we can observe. We simply don't know because we can only see the portion of it that's within our cosmic horizon. The James Webb Space Telescope, with its unprecedented infrared vision, has pushed our observational frontier closer to this ultimate limit than ever before. In 2023 and 2024, JWST has been detecting galaxies that formed when the universe was less than 400 million years old, bringing us tantalizingly close to the cosmic dark ages that preceded the formation of the first star. But even JWST has fundamental limits. As we look at more and more distant objects, they appear fainter, redder, and more stretched by cosmic expansion. Eventually, we reach a point where even the most powerful telescopes cannot gather enough photons to form an image. This isn't a technological limitation that we can overcome with bigger mirrors or better detectors. It's the fundamental consequence of the expansion of the universe and the finite speed of light. So when we ask how far we can see in the universe, the answer depends on what we mean by see. If we mean observe with traditional electromagnetic radiation, our ultimate horizon, is the cosmic microwave background, 13.8 billion years ago in time and 46.5 billion light-years away in distance. But as we'll discover, there are other ways to probe even farther back, using cosmic messengers that were born in the very first moments after the Big Bang and have been traveling through space ever since, carrying secrets from epochs that no telescope will ever illuminate. Standing at the edge of human vision requires more than just curiosity. It demands instruments that can capture the faintest whispers of light from the most distant reaches of space and time. The story of how far we can see is really the story of how we've learned to amplify our cosmic senses far beyond what evolution ever intended. When Galileo first pointed his simple telescope at the night sky in 1609, he was working with an instrument that could gather just a few times more light than the human eye. Today, our most powerful telescopes collect millions of times more light than Galileo's crude refractor, and they can detect electromagnetic radiation across the entire spectrum, from radio waves longer than buildings to gamma rays more energetic than anything we can produce on Earth. The fundamental challenge of cosmic observation is signal detection. Light from distant galaxies is incredibly faint by the time it reaches us. Consider this: the total amount of energy that all the telescopes on Earth have ever collected from sources beyond our solar system is less than the energy of a single snowflake hitting the ground. We're literally trying to study the universe one photon at a time. This is why telescope size matters so much. The light-gathering power of a telescope increases with the square of its diameter. Double the diameter, and you collect 4 times as much light. The largest ground-based telescopes today, like the twin 10-meter Keck telescopes in Hawaii, can collect about 25 million times more light than the human eye. But even these giants struggle to see the most distant objects in the universe. The problem isn't just faintness, it's also atmosphere. Earth's atmosphere is constantly moving, creating turbulence that blurs and distorts the light from celestial objects. It's like trying to read a book at the bottom of a swimming pool while someone is making waves. This is why the sharpest images of distant galaxies come from space-based telescopes, like the Hubble Space Telescope, which orbits above the atmosphere in the perfect vacuum of space. But Hubble, remarkable as it is, sees primarily invisible light and near-infrared. For the deepest cosmic observations, we need to look in the infrared part of the spectrum. Here's why. As light travels through expanding space, its wavelength gets stretched. Light that was emitted as visible blue light from a galaxy in the early universe reaches us as infrared radiation. The more distant the galaxy, the more its light is redshifted toward longer wavelengths. This is where the James Webb Space Telescope revolutionized our cosmic vision. Launched in late 2021, JWST is optimized for infrared observation, with a primary mirror 6.5 meters across, nearly 3 times the diameter of Hubble's. But size isn't its only advantage. JWST operates at extremely cold temperatures, about minus 370 degrees Fahrenheit, which prevents thermal radiation from the telescope itself from overwhelming the faint infrared signals from distant galaxies. The results have been extraordinary. Within its first year of operation, JWST was detecting galaxies that formed when the universe was only 300 to 400 million years old. These galaxies appear as tiny red dots in JWST's images, but they represent some of the first large structures to form after the cosmic dark ages following recombination. However, even JWST has limits. As we look to more and more distant objects, several factors conspire to make detection increasingly difficult. First, the inverse square law means that objects appear dimmer as the square of their distance. A galaxy twice as far away appears 4 times fainter. Second, the expansion of the universe stretches light to longer wavelengths, spreading a galaxy's light across a broader spectrum and making it appear dimmer at any given wavelength. Third, cosmological time dilation means that processes in distant galaxies appear to run in slow motion, further reducing the apparent brightness. But the real limit isn't technological, it's fundamental. As we approach the cosmic microwave background, we're approaching the moment when the universe became transparent. Before recombination, at redshifts greater than about 1/100, the universe was opaque to electromagnetic radiation. No amount of technological advancement will allow us to see farther back in time using traditional telescopes, because there's simply nothing to see. The light hasn't had time to reach us, and even if it had, it would have been absorbed by the opaque plasma that filled the early universe. This is where the story gets creative. If we can't see farther with light, what other cosmic messengers might carry information from even earlier times? The answer lies in some of the most exotic physics we know: neutrinos, gravitational waves, and hypothetical relics from the earliest moments of cosmic history. Neutrinos are ghostly particles that barely interact with matter. They're produced in enormous numbers by nuclear reactions in stars, and they stream through space almost unimpeded. Trillions of neutrinos pass through your body every second, but they're so weakly interacting that they rarely bump into anything. This makes them incredibly difficult to detect. But it also means they can carry information from places and times that light cannot reach. The universe should be filled with relic neutrinos from the Big Bang itself, produced when the universe was just 1 second old. These cosmic neutrinos have been cooling and redshifting as the universe expanded, and today they should have a temperature of just 1.9 degrees above absolute zero. If we could detect these relic neutrinos, they would give us a direct view of the universe when it was far younger and denser than what we can see with any telescope. Unfortunately, detecting relic neutrinos is extraordinarily challenging. They have such low energies and interact so weakly that no current technology can reliably detect them. But physicists are working on it. Future neutrino observatories might use vast amounts of material, perhaps thousands of tons of liquid argon or water, deep underground to shield from cosmic rays, waiting for the rare interactions that would signal the detection of a relic neutrino from the Big Bang. Even more exotic are gravitational waves, ripples in spacetime itself, predicted by Einstein and first detected in 2015 by the LIGO experiment. Gravitational waves travel at the speed of light, but unlike electromagnetic radiation, they interact so weakly with matter that they pass through everything essentially unchanged. A gravitational wave that started its journey in the early universe would reach us today with almost no modification from its passage through cosmic history. The current generation of gravitational wave detectors, including LIGO and Virgo, can detect waves from colliding black holes and neutron stars. But these events occurred relatively recently in cosmic history. To probe the early universe with gravitational waves, we need to detect much more ancient signals, perhaps from cosmic inflation itself or from phase transitions in the first fraction of a second after the Big Bang. Future space-based gravitational wave detectors, like the planned LISA mission, will be sensitive to lower-frequency gravitational waves that could carry information from much earlier epochs. These detectors will consist of multiple spacecraft flying in formation, connected by laser beams that can measure changes in distance smaller than 1,000th the width of a proton. But perhaps the most tantalizing prospect for seeing beyond. The CMB lies in the polarization of the cosmic microwave background itself. While the CMB represents the farthest we can see with direct light, it may contain indirect evidence of even earlier epochs encoded in its polarization patterns. During cosmic inflation, the brief period of exponential expansion that preceded the hot Big Bang, quantum fluctuations in the gravitational field would have produced gravitational waves. These primordial gravitational waves would have left a characteristic signature in the polarization of the CMB, like a fossil fingerprint of the universe's first moment. Several experiments, including ground-based telescopes in Antarctica and future space missions, are designed to detect this polarization signature. If successful, they would effectively extend our vision back to the inflationary epoch, perhaps 10 further 32 seconds after the Big Bang, when the observable universe was smaller than a proton. The technology required for these observations pushes the limits of what's physically possible. The polarization signal from primordial gravitational waves would be incredibly faint, perhaps just a few parts in a million of the total CMB signal. Detecting it requires exquisite control of systematic errors and the ability to distinguish the primordial signal from contamination by our own galaxy's magnetic field and dust. Current and future CMB experiments use arrays of thousands of superconducting detectors cooled to just a fraction of a degree above absolute zero. These detectors can measure the arrival time of individual photons and determine their polarization with extraordinary precision. The data analysis requires supercomputers to process petabytes of information and sophisticated algorithms to separate the cosmological signal from terrestrial interference. But even if we successfully detect the polarization signature of primordial gravitational waves, there are still earlier epochs that might remain forever beyond our reach. The very first moments after the Big Bang, when the universe underwent cosmic inflation, involve physics beyond our current understanding. The energies and temperatures were so extreme that our theories of particle physics and gravity may not apply. Some physicists speculate about even more exotic probes of the earliest universe. Perhaps cosmic strings, one-dimensional defects in space-time that might have formed during phase transitions in the early universe, could provide observable signatures, or maybe magnetic monopoles, hypothetical particles that would have been produced in grand unified theories, could carry information from the universe's birth. There's also the intriguing possibility that the universe itself preserves information about its earliest moments in ways we haven't yet imagined. Some theories suggest that quantum entanglement might create long-range correlations that encode information about initial conditions. Others propose that the vacuum state of quantum fields might retain memory of primordial events. As we push the boundaries of cosmic observation ever further, we're forced to confront fundamental questions about the nature of information and causality. Is there a limit to how much we can know about the universe's history? Are there epochs so early that they're not just observationally inaccessible but conceptually unknowable? The quest to see farther into the universe is ultimately a quest to understand our cosmic origins. Each new generation of instruments brings us closer to the ultimate horizon, but it also reveals new mysteries and new limits. We're like explorers approaching the edge of an ancient map, where the familiar territory gives way to regions marked, "Here be dragons." But that's what makes this journey so compelling. We're not just building bigger telescopes to see more galaxies. We're developing the tools to probe the deepest questions about existence itself. How did space and time begin? What determined the fundamental constants of nature? Are we part of a larger multiverse that extends far beyond our cosmic horizon? The technology of cosmic vision is rapidly approaching fundamental limits imposed by the laws of physics themselves. But as we'll discover, those limits are far stranger and more profound than simple distance measurements. They touch on the very nature of information, causality, and the relationship between observer and observed in a universe that may be far weirder than we've ever imagined. The concept of an observable universe might seem straightforward at first glance. After all, if the universe has existed for 13.8 billion years and light travels at a finite speed, then we should be able to see objects whose light has been traveling for up to 13.8 billion years. But as we're about to discover, the reality is far more complex and far more fascinating than this simple calculation would suggest. The observable universe isn't just a sphere of space around us with a radius of 13.8 billion light-years. It's a dynamic, evolving concept that depends on the expansion of space, the history of cosmic transparency, and the fundamental properties of spacetime itself. To understand its true boundaries, we need to think carefully about what it means to observe something in an expanding universe. Let's start with a thought experiment. Imagine you're standing in the center of a vast, dark plain, and people are lighting torches at various distances around you. Each torch represents a galaxy, and the light from the torch represents the electromagnetic radiation we receive from that galaxy. Now imagine that the plane itself is expanding, carrying the torchbearers away from you at speeds that increase with distance. This is essentially what we see when we look out into the universe. But there's a crucial detail. The torches weren't all lit at the same time. In our cosmic analogy, the farther away a torch is, the earlier it was lit. The most distant torches were lit when the universe was very young, and their light has been traveling toward us ever since, fighting against the expansion of space. The boundary of our observable universe is defined by the most distant sources whose light could have reached us by now. This boundary is called the particle horizon, and it represents the farthest distance from which light could have traveled since the beginning of time. But calculating this distance requires careful accounting for the expansion of the universe throughout cosmic history. When cosmologists first worked out these calculations in detail, they discovered something remarkable. Due to the expansion of space, the most distant observable objects are now much farther away than their light travel distance would suggest. An object whose light has taken 13 billion years to reach us is now approximately 30 billion light-years away. The current edge of our observable universe, corresponding to light emitted just 380,000 years after the Big Bang, is now about 46.5 billion light-years away. This means the observable universe has a diameter of approximately 93 billion light-years. It's a sphere of space-time with us at the center, but not because we're special. Every observer in the universe sits at the center of their own observable universe, their own cosmic horizon defined by how far light could have traveled to reach them. But here's where things get mind-bending. The edge of our observable universe isn't a place, it's an event. It's the cosmic microwave background, the moment when the universe became transparent and photons could travel freely through space for the first time. This surface of last scattering surrounds us like a vast, distant shell. But it's not a physical object. It's a moment in time preserved across space by the finite speed of light. Every day, this cosmic horizon expands. Light from regions that were previously beyond our reach crosses into our observable sphere. The boundary moves outward at the speed of light, approximately 186,000 miles per second, or about 6 trillion miles per year. This means that every year we can see light from regions that are now about 6 trillion miles farther away. But due to cosmic expansion, those regions are actually much more distant than this simple calculation would suggest. The expansion of our observable universe reveals something profound about the nature of cosmic horizons. They're not static barriers, but dynamic boundaries that evolve with time. As we watch, previously invisible regions of the universe come into view, like a cosmic dawn breaking over an ever-expanding landscape. But there's another type of horizon that's even more mysterious: the event horizon. While the particle horizon defines how far we can see into the past, the event horizon defines how far we can influence the future. Due to the accelerating expansion of space, there are regions of the universe from which light emitted today will never reach us, no matter how long we wait. This acceleration is driven by dark energy, a mysterious component that makes up about 68% of the universe's total energy density. Dark energy acts like a cosmic repulsion, pushing space apart at an ever-increasing rate. As a result, distant galaxies aren't just moving away from us, they're accelerating away from us. The existence of dark energy creates what cosmologists call the cosmic event horizon. Currently, this horizon is located at a distance of approximately 16 billion light-years. Galaxies beyond this distance are receding from us so rapidly that light they emit today will never reach us. In fact, light emitted from these galaxies in the past is only now reaching us because space was expanding more slowly in the past than it is today. Think about what this means. There are galaxies in our observable universe that we can see today, but if they emit light now, that light will never reach us. We're seeing them as they were billions of years ago, but we're cut off from their present and future. It's like watching a movie of someone's past while knowing you'll never see how their story ends. This creates a poignant cosmic irony. As time passes, our observable universe grows larger as light from more distant regions reaches us. But simultaneously, our potential for future observation shrinks as dark energy carries more and more galaxies beyond our event horizon. We're in a race between the expansion of our past light cone and the contraction of our future light cone. The situation becomes even stranger when we consider what this means for cosmic evolution. The galaxies we see today at the edge of our observable universe are not representative of what the universe looks like at those distances right now. We're seeing them as they were when the universe was young, when stars were just beginning to form and galaxies were small, chaotic systems very different from the mature spiral and elliptical galaxies we see nearby. But what do those distant regions look like today? We'll never know. By the time light from their current state could reach us, the universe will have expanded so much that they'll be far beyond our event horizon. We're forever locked out of knowing the present state of the most distant observable galaxies. This raises profound questions about the nature of cosmic knowledge. Is there information about the universe that is, in principle, unknowable? The answer appears to be yes. The accelerating expansion of space means that there are aspects of cosmic reality that will remain forever beyond our reach, not because of technological limitations, but because of the fundamental structure of spacetime itself. Recent observations have provided tantalizing glimpses of structures that may extend beyond our observable universe. The cosmic microwave background shows slight temperature variations that correspond to the seeds of all cosmic structure. But detailed analysis of these patterns suggests that they may be influenced by much larger structures that extend far beyond our cosmic horizon. Some cosmologists have argued that the CMB patterns show evidence of dark flow, a coherent motion of galaxy clusters over scales much larger than our observable universe. If this interpretation is correct, it would suggest that our observable universe is just a small part of a much larger cosmic structure, like a small region in a vast ocean with currents driven by continents we cannot see. The idea that structure extends beyond our cosmic horizon is supported by theoretical considerations as well. Models of cosmic inflation suggest that the universe underwent a period of exponential expansion in its earliest moments, growing from subatomic to macroscopic scales in a tiny fraction of a second. This inflationary expansion would have created a universe much larger than our observable portion, with the same physical laws and similar structures extending far beyond our horizon. If inflation is correct, then our observable universe is just a tiny bubble in an immense cosmic ocean. The total size of the universe could be thousands, millions, or even infinitely larger than what we can observe. We're like microbes on a soap bubble, able to see only a small patch of the surface while remaining ignorant of the vast sphere that extends beyond our vision. But even more exotic possibilities exist. Some versions of inflation theory suggest that different regions of the universe might have different physical properties. The fundamental constants of nature, the masses of particles, even the number of spatial dimensions might vary from region to region. Our observable universe might have the properties it does simply because we exist in a region where those properties allow for the formation of stars, planets, and life. This leads to the concept of the multiverse, a vast ensemble of regions with different physical properties. Most of these regions would be sterile, unable to support the complex chemistry required for life. But in a universe large enough, there would be regions like ours where the conditions are just right for complexity and consciousness to emerge. The boundaries of our observable universe also raise questions about the nature of infinity. If the universe is infinite in extent, then there are infinitely many regions like our observable universe scattered throughout space. Some of these regions would be nearly identical to ours, with the same galaxies, stars, and planets arranged in almost the same way. Others would be completely different, with entirely alien physics and unimaginable forms of matter and energy. But infinity is a difficult concept to grasp, especially when applied to physical reality. How can we ever know if the universe is truly infinite? By definition, infinity extends beyond any finite observation. We might see patterns in the cosmic microwave background that suggest infinite extent, but we can never directly observe infinity itself. Current observations are consistent, with a flat universe that extends infinitely in all directions. If this is correct, then our observable universe is just one of infinitely many similar regions, each surrounded by its own cosmic horizon, each containing its own collection of galaxies, stars, and perhaps civilizations asking the same questions we're asking now. As we push our observations closer to the cosmic microwave background, we're approaching the ultimate boundary of electromagnetic observation. Beyond this boundary lies the cosmic dark ages, a period when the universe was opaque and no light could travel freely. But even this isn't the ultimate boundary of cosmic knowledge. Gravitational waves, neutrinos, and perhaps other exotic particles carry information from even earlier epochs. The quest to understand the boundaries of the observable universe is ultimately a quest to understand the limits of knowledge itself. What can we know about reality? What must forever remain hidden? As we stand at the edge of our cosmic horizon, we're confronting not just the physical boundaries of space and time, but the conceptual boundaries of human understanding. The observable universe is both vast beyond imagination and surprisingly small compared to what might lie beyond. It's a cosmic bubble of light and information in an ocean of mystery that may extend far beyond our wildest dreams. As we peer toward its edges, we're reminded that every answer in cosmology reveals new questions, and every boundary we approach opens up vistas of even greater mystery. Standing at the edge of what we can see with light, we discover that the universe has been sending us other messages all along. While photons carry the stories written in starlight, there are cosmic messengers that began their journeys much earlier, traveling through eras when the universe was too young and too opaque for light to escape. These messengers carry secrets from the universe's infancy, from times when space itself was being forged in the crucible of creation. The most abundant of these invisible messengers are neutrinos, ghostly particles so elusive that trillions pass through your body every second without leaving a trace. They're born in the nuclear furnaces of stars, in the violent explosions of supernovas, and most remarkably, in the primordial moments of the Big Bang itself. Unlike light, which was trapped in the cosmic plasma for 380,000 years after the Big Bang, neutrinos could travel freely through the early universe almost from the very beginning. Picture the universe when it was just 1 second old. The temperature was about 10 billion degrees, hot enough to forge the light elements that would become the raw materials for stars and galaxies. At this cosmic moment, when the universe was 1 trillion times smaller than it is today, neutrinos decoupled from the primordial soup and began streaming freely through space. They've been traveling ever since, cooling and stretching with the expansion of the universe, carrying with them a direct record of conditions when the cosmos was in its infancy. These relic neutrinos should still be with us today, forming what cosmologists call the cosmic neutrino background, or CNB. Just as the cosmic microwave background gives us a snapshot of the universe at 380,000 years old, the CNB would give us a snapshot from when the universe was just 1 second old. It would be like finding a fossil from the first moment of life on Earth, but for the entire cosmos. The challenge is that these relic neutrinos have been redshifted to incredibly low energies by billions of years of cosmic expansion. Today, they should have temperatures of just 1.9 degrees above absolute zero, making them extraordinarily difficult to detect. A typical relic neutrino carries about 100,000 times less energy than the photons in the cosmic microwave background. It's like trying to hear a whisper in a thunderstorm. Yet physicists are working on experiments that might, within the next few decades, achieve the impossible. Direct detection of the cosmic neutrino background. These experiments require massive detectors, often containing thousands of tons of liquid argon or water, buried deep underground to shield them from cosmic rays and other background radiation. The Katrin experiment in Germany is pushing the boundaries of neutrino mass measurement, while future projects like Ptolemy aim to detect relic neutrinos directly. But neutrinos aren't the only messengers from the universe's earliest epochs. Even more exotic are gravitational waves, ripples in space-time itself, that carry information from some of the most violent and energetic events in cosmic history. When Einstein first predicted gravitational waves in 1915, he thought they would be far too weak to ever detect. It took exactly 1 century before the LIGO experiment proved him wrong, detecting gravitational waves from 2 colliding black holes located 1.3 billion light-years away. The detection of gravitational waves opened an entirely new window on the universe. Unlike electromagnetic radiation, which can be absorbed, scattered, or blocked by intervening matter, gravitational waves pass through everything essentially unchanged. They're like cosmic X-rays that can see through the entire universe, carrying pristine information from their sources across billions of years of cosmic history. Current gravitational wave detectors like LIGO and Virgo are sensitive to waves from relatively recent cosmic events. Colliding black holes and neutron stars that formed when the universe was already mature. The real prize lies in detecting much more ancient gravitational waves, signals that could carry information from the universe's first moments. During cosmic inflation, the brief period of exponential expansion that preceded the hot Big Bang, quantum fluctuations in the gravitational field itself would have generated a background of primordial gravitational waves. These waves would have been stretched by inflation to enormous wavelengths, creating a fossil record of the universe when it was just 10 dirty ton to 32 seconds old, a time when the observable universe was smaller than a proton. Think about what this means. If we could detect primordial gravitational waves, we would be observing the universe from an epoch so early that our current physics barely applies. We would be seeing the afterglow of the process that created space and time themselves, the cosmic equivalent of watching the moment when existence began. The search for these primordial waves focuses on their effect on the cosmic microwave background. As these ancient gravitational waves propagated through the early universe, they would have created a characteristic pattern of polarization in the CMB, like fingerprints left in the cosmic afterglow. Several experiments, including ground-based telescopes in Antarctica and planned space missions, are designed to detect this incredibly faint signature. The challenge is extraordinary. The polarization signal from primordial gravitational waves would be just a few parts in a million of the total CMB signal. It's like trying to detect the shadow of a butterfly on the moon while standing on Earth. The experiments require superconducting detectors cooled to a fraction of a degree above absolute zero, sophisticated algorithms to remove contamination from our galaxy's own magnetic field, and years of careful observations to build up enough signal to overcome the noise. But even gravitational waves may not represent the ultimate frontier of cosmic archaeology. Some physicists speculate about even more exotic relics from the universe's birth, particles and fields that could carry information from epochs so early that we don't yet have theories to describe them. One possibility is cosmic strings, one-dimensional, defects in spacetime that might have formed during phase transitions in the early universe. These hypothetical objects would be incredibly thin, perhaps smaller than a proton in diameter, but they could stretch across entire galaxies. If cosmic strings exist, they would oscillate and generate gravitational waves with distinctive signatures that could be detected by future gravitational wave observatories. Another speculative possibility involves magnetic monopoles, hypothetical particles that would carry isolated magnetic charges. While ordinary magnets always have both north and south poles, monopoles would have only one type of magnetic charge. They're predicted by some grand unified theories of particle physics, and if they exist, they would have been produced in vast numbers during the universe's first moments. The problem with magnetic monopoles is that we don't see them today, which creates what physicists call the monopole problem. Cosmic inflation provides a potential solution. If monopoles were produced before inflation began, the exponential expansion would have diluted their density to undetectable levels. But this also means that detecting relic monopoles would provide direct evidence for both grand unification and cosmic inflation. Even more exotic are hypothetical particles called Axions, which could solve both the strong CP problem in particle physics and provide a candidate for dark matter. If Axions exist and were produced in the early universe, they could form a cosmic background similar to the neutrino background, but potentially easier to detect with specialized experiments. The search for these cosmic relics pushes experimental physics to its absolute limits. Dark matter detection experiments, buried in mines thousands of feet underground, wait for the rare interactions that might signal the passage of a dark matter particle through their detectors. These experiments must be so sensitive that they can detect the recoil of a single atomic nucleus, yet so well shielded that they're unaffected by cosmic rays, radioactivity, and even the vibrations from distant earthquakes. Axion detection experiments, like the Axion Dark Matter Experiment, ADMX, use powerful magnetic fields and ultra-sensitive microwave receivers to search for the conversion of axions into photons. The signals they're looking for are so weak that the experiments must operate at temperatures colder than interstellar space and in magnetic fields thousands of times stronger than Earth's. But perhaps the most mind-bending possibility for probing the early universe involves quantum mechanics itself. Some physicists have proposed that quantum entanglement might preserve information about the universe's initial conditions in ways that could, in principle, be accessed today. The idea is that quantum correlations established during inflation might persist across cosmic distances, creating a kind of quantum fossil record of the universe's birth. This concept pushes quantum mechanics into uncharted territory. If quantum entanglement can indeed preserve information about cosmic initial conditions, it would suggest that the universe itself is a kind of quantum computer, storing and processing information on scales we can barely imagine. The implications would be profound, potentially connecting quantum mechanics, cosmology, and information theory in ways that could revolutionize our understanding of reality itself. The search for information from the pre-CMB universe also raises deep questions about the nature of causality and observation. In quantum mechanics, the act of observation plays a fundamental role in determining physical reality. But what does it mean to observe the universe from an epoch before observers existed? Some interpretations of quantum mechanics suggest that conscious observation might be required to collapse quantum superpositions into definite states. If so, then perhaps our current observations of cosmic relics are actually determining the nature of the universe's past, creating a kind of temporal feedback loop between past and present. These ideas push us to the very edge of scientific speculation, into realms where physics, philosophy, and metaphysics begin to blur together. But they're not merely abstract theorizing. Real experiments are being designed to test some of these concepts, using the quantum properties of the cosmic microwave background and other cosmic relics to probe the foundations of quantum mechanics on cosmological scales. The European Space Agency's Planck satellite, which operated from 2009 to 2013, provided the most detailed map of the cosmic microwave background ever made. The data from Planck has allowed cosmologists to test theories of inflation, measure the geometry of space, and constrain the properties of dark matter and dark energy with unprecedented precision. Future missions, like the proposed Lightbird satellite, will search for the elusive signature of primordial gravitational waves with even greater sensitivity. Ground-based experiments are also pushing the boundaries of what's possible. The South Pole Telescope, BICEP, and other experiments in Antarctica take advantage of the dry, stable atmosphere at the bottom of the world to make incredibly precise measurements of CMB polarization. These experiments have ruled out some models of inflation and placed tight constraints on others, gradually narrowing down the possible scenarios for the universe's birth. But even as we push our observations to earlier and earlier epochs, we're forced to confront fundamental limits imposed by physics itself. Quantum mechanics suggests that space-time itself becomes uncertain at scales smaller than the Planck length, about 10 to 35 meters. At energies corresponding to the Planck scale, our current theories of physics break down completely. This might represent an absolute limit to how far back in time we can probe, a kind of quantum event horizon beyond which the very concept of observation loses meaning. Yet even this ultimate limit might not be final. Some speculative theories, like loop quantum gravity and string theory, attempt to describe physics at the Planck scale and beyond. These theories suggest that space-time itself might have a discrete, granular structure at the smallest scales, or that our three-dimensional space might be a projection from a higher dimensional realm. If these theories are correct, they might provide new ways to extract information about the universe's earliest moments. Perhaps the structure of space-time itself preserves a record of cosmic initial conditions, encoded in patterns too subtle for current experiments to detect but potentially accessible to future technologies we can barely imagine. The quest to see beyond the visible universe is ultimately a quest to understand the deepest laws of nature. Every cosmic messenger we detect, from neutrinos to gravitational waves to hypothetical axions, carries information not just about cosmic history, but about the fundamental structure of reality itself. We're not just building better detectors, we're developing new ways to ask questions about existence. As we stand at the frontier of cosmic observation, we're reminded that the universe is far stranger and more wonderful than our ancestors could have imagined. We live in a cosmos filled with invisible messengers carrying news from the dawn of time, where the act of observation might determine the nature of reality, and where the ultimate limits of knowledge touch on the very foundations of space, time, and consciousness itself. As we push against the boundaries of cosmic observation, we encounter something far more profound than technological limitations or the finite speed of light. We discover that the universe itself appears to have built-in limits to what can be known, boundaries written into the very fabric of reality that no amount of scientific advancement can overcome. These ultimate horizons challenge our most basic assumptions about knowledge, causality, and the nature of information itself. The story begins with a simple but profound realization. In an expanding universe, not all information can reach all observers. This isn't just a practical limitation. It's a fundamental feature of space-time geometry. Just as the event horizon of a black hole creates a boundary beyond which information cannot escape, the accelerating expansion of space creates cosmic horizons that permanently separate different regions of the universe from causal contact. Consider what this means for the flow of information through the cosmos. Information can only travel at the speed of light, but space itself can expand at any rate. When the expansion rate becomes large enough, it creates regions that are causally disconnected forever. Light emitted from these regions today will never reach us, no matter how long we wait. They exist in a kind of cosmic exile, cut off from our ability to observe or influence them. This creates what physicists call the causal horizon, a boundary that separates the events we can potentially influence from those that are forever, beyond our reach. But the existence of causal horizons raises deep questions about the nature of reality itself. If there are regions of the universe that we can never observe or interact with, in what sense can we say they exist? Do unobservable regions of the universe have the same ontological status as the regions we can see? These questions become even more puzzling when we consider the role of information in quantum mechanics. In quantum theory, information plays a fundamental role in determining physical reality. The quantum state of a system contains all the information needed to predict the probabilities of different measurement outcomes. But what happens to quantum information when it crosses a causal horizon? The puzzle deepens when we consider the concept of quantum entanglement. Two particles can become entangled in such a way that measuring one instantaneously affects the other, regardless of the distance between them. Einstein famously called this spooky action at a distance, but experiments have confirmed that quantum entanglement is real. However, it cannot be used to transmit information faster than light, which preserves the principle of causality. But what if entangled particles are separated by cosmic expansion until they're beyond each other's causal horizons? Do they remain entangled? If so, this would mean that the universe contains quantum correlations that span regions that can never communicate with each other. The implications are mind-bending. The universe might be fundamentally non-local in ways that transcend even our current understanding of quantum mechanics. Some physicists have proposed that quantum entanglement might provide a way to extract information from beyond causal horizons. The idea is that entangled particles created in the early universe might preserve correlations that encode information about regions now beyond our cosmic horizon. By studying the quantum properties of particles in our observable universe, we might be able to infer the properties of regions we can never directly observe. This concept pushes quantum mechanics into uncharted territory. It suggests that the universe might be a vast quantum computer, with information about unobservable regions encoded in the quantum states of observable particles. The challenge is developing the theoretical and experimental tools to decode this information, assuming it exists at all. But perhaps the most profound limit to cosmic knowledge comes from the nature of space-time itself at the smallest scales. Quantum mechanics and general relativity suggest that space-time becomes fundamentally uncertain at the Planck scale, where distances are about 10 feet, and time intervals are about 10 to 43 seconds. At these scales, the very concepts of space and time begin to break down. This creates what might be called the quantum horizon, a fundamental limit to how precisely we can probe the structure of space-time. Below the Planck scale, the notion of a smooth, continuous space-time gives way to a foamy, probabilistic quantum geometry where cause and effect become uncertain. This might represent an absolute limit to reductionist science, a scale beyond which the very concept of measurement becomes meaningless. Yet even this ultimate limit might not be final. Some theories of quantum gravity, like loop quantum gravity and causal set theory, suggest that space-time has a discrete, granular structure at the Planck scale. If these theories are correct, they might provide new ways to extract information about the universe's earliest moments, even from epochs when classical space-time concepts don't apply. String theory takes this even further, suggesting that our familiar three-dimensional space might be a projection from a higher dimensional realm. In this view, all the information about our universe might be encoded on a distant boundary, like a cosmic hologram. This holographic principle has profound implications for the nature of information and reality, suggesting that what we perceive as three-dimensional space might be an illusion created by information processing on a two-dimensional surface. This holographic principle also provides a potential solution to one of the deepest puzzles in cosmology, the information paradox. If the universe contains regions beyond our causal horizon, what happens to the information in those regions? Is it lost forever, or is it somehow preserved in a form we can access? The holographic principle suggests that all information might be encoded on cosmic horizons, potentially making it accessible even when the regions themselves are not. But the quest to understand ultimate horizons also forces us to confront the role of consciousness and observation in determining reality. In some interpretations of quantum mechanics, conscious observation plays a fundamental role in collapsing quantum superpositions into definite states. If this is correct, then the act of observation might literally create the reality we observe. This raises profound questions about the nature of cosmic knowledge. If conscious observation is required to determine physical reality, then perhaps the history of the universe is not fixed, but is continually being determined by current observations. The cosmic microwave background, for instance, might not be a record of what happened 380,000 years after the Big Bang, but rather a quantum superposition of all possible histories that gets collapsed into a definite state only when we observe. Indeed, these ideas push us to the very edge of scientific discourse, into realms where physics, philosophy, and metaphysics become indistinguishable. But they're not merely abstract speculation. Real experiments are being designed to test the role of observation in quantum mechanics on cosmological scales. Using the cosmic microwave background and other cosmic phenomena as laboratories for testing the foundations of quantum theory. The recent development of quantum information theory has also provided new tools for thinking about cosmic horizons. Concepts like quantum error correction, quantum computing, and quantum communication might have applications to cosmology that we're only beginning to understand. Perhaps the universe itself is a kind of quantum computer, processing information about its own state and evolution in ways that transcend our current understanding of computation and information. One particularly intriguing possibility involves the concept of quantum error correction in cosmology. Just as quantum computers use error correction codes to preserve quantum information despite environmental interference, the universe might use similar mechanisms to preserve information about its initial conditions despite cosmic expansion and other sources of decoherence. If so, this information might be accessible through careful analysis of cosmic observables, even when the original sources are beyond our causal horizon. The emerging field of quantum cosmology is exploring these connections between quantum information and cosmic evolution. Some researchers are investigating whether the universe's apparent fine-tuning for life might be a consequence of quantum selection effects, where the act of observation by conscious beings selects for cosmic parameters compatible with the existence of observers. Others are exploring whether quantum entanglement might create a kind of cosmic consciousness, connecting all observers in the universe through invisible quantum correlations. These ideas remain highly speculative, but they point toward a deeper understanding of the relationship between mind and cosmos. If consciousness plays a fundamental role in determining physical reality, then the limits of cosmic knowledge might not be imposed by physics alone, but by the nature of conscious observation itself. The search for ultimate horizons also intersects with questions about the nature of mathematical truth and physical reality. Mathematics seems to describe the universe with uncanny accuracy, leading some physicists to wonder whether mathematical structures might be more fundamental than physical objects. In this view, the universe might be a mathematical structure that exists independently of physical space and time. If mathematics is indeed fundamental, then the limits of cosmic knowledge might be determined not by physical horizons, but by the structure of mathematical truth itself. Some mathematical truths might be inherently unknowable, not because of physical limitations, but because of the logical structure of mathematics. Gödel's incompleteness theorems, for instance, show that some mathematical truths cannot be proven within any finite formal system. Perhaps similar limitations apply to our understanding of cosmic reality. The concept of mathematical infinity also plays a crucial role in cosmology. If the universe is infinite in extent, then it contains infinitely many regions like our observable universe, each with its own collection of galaxies, stars, and potentially civilizations. But infinity is a notoriously difficult concept to grasp, both mathematically and physically. How can we ever verify that the universe is truly infinite? By definition, infinity extends beyond any finite observation. Some cosmologists have proposed that the universe might be finite but unbounded, like the surface of a sphere but in higher dimensions. In such a universe, Traveling far enough in any direction would eventually bring you back to your starting point. This would eliminate the problems associated with infinite space, while still allowing for a universe without edges or boundaries. Recent observations of the cosmic microwave background have searched for evidence of such cosmic topology, looking for patterns that would indicate we're seeing the same regions of space from different directions. So far, no such patterns have been found, but the search continues. If the universe does have a finite, closed topology, it would place ultimate limits on the amount of information it can contain. The nature of time also plays a crucial role in determining cosmic horizons. In Einstein's theory of relativity, time is not absolute, but depends on the observer's motion and the strength of gravitational fields. This means that different observers might disagree about the simultaneity of events and the rate at which time passes. But what does this mean for cosmic knowledge? If time itself is relative, then perhaps the limits of knowledge are also relative to the observer. Some theories of quantum gravity suggest that time itself might emerge from more fundamental quantum processes. In this view, time is not a fundamental feature of reality, but rather an emergent property that arises from the quantum dynamics of information. If time is indeed emergent, then the concept of cosmic horizons might need to be completely reconsidered. As we push against the ultimate limits of cosmic knowledge, we're forced to confront the possibility that some questions might be fundamentally unanswerable. There might be aspects of reality that are not just practically inaccessible but logically unknowable. This doesn't represent a failure of science, but rather a recognition of the deep connections between knowledge, reality, and consciousness. Yet, even as we acknowledge these ultimate limits, we continue to push forward, developing new theories, designing new experiments, and asking new questions. The quest to understand cosmic horizons is ultimately a quest to understand ourselves, our place in the universe, and the nature of knowledge itself. As we stand at the edge of the knowable, we're reminded that the universe is far stranger and more wonderful than we ever imagined, and that the greatest discoveries might await us not in the distant cosmos, but in the deep connections between mind, mathematics, and the structure of reality itself. Here we are, back on our mountaintop, but now those simple binoculars in your hands represent something far more profound than when we began this journey. You raise them to your eyes one more time, but now you understand that you're not just looking across space, you're peering backward through the entire history of existence, touching the very moment when the universe first became transparent to light. Those distant stars that twinkle before you are no longer just points of light. They're time machines, each photon carrying messages from the past, some from millions of years ago, others from billions. And beyond them, at the very edge of what any telescope could ever see, lies the cosmic microwave background, the afterglow of creation itself, the echo of the Big Bang still reverberating through space after nearly 14 billion years. But now you know the deepest secret of cosmic vision. The farthest we can see isn't determined by the power of our instruments, but by the fundamental structure of the universe itself. At a distance of 46.5 billion light-years, we encounter an absolute horizon, a wall of light from the moment when atoms first formed and the cosmic fog lifted. Beyond that boundary lies a realm that no electromagnetic telescope will ever illuminate. Not because we lack the technology, but because the light simply doesn't exist to be seen. Yet even this isn't the end of the story. Ghostly neutrinos whisper secrets from when the universe was just 1 second old. Gravitational waves carry news from epochs so early that space and time themselves were being forged, and perhaps encoded in the quantum correlations of particles. Around us lies information about regions of the cosmos that exist beyond our cosmic horizon, forever separated from us by the accelerating expansion of space. As you lower those binoculars, consider this. Every photon that enters your eyes, whether from a distant galaxy or from the lamp beside you, has traveled a unique path through spacetime to reach you at this exact moment. You are standing at the center of your own observable universe, a sphere of spacetime 93 billion light-years across, containing perhaps 2 trillion galaxies, each with billions of stars, and quite possibly civilizations asking the same questions. We've explored tonight, but the most remarkable thing isn't the vast scale of what we can see. It's the fact that we can see it at all. The universe has given conscious beings like us the ability to look back toward our own cosmic origins, to decode the light of creation, and to ask questions that push against the very limits of knowledge itself. So the next time you step outside on a clear night and gaze up at the stars, remember that you're not just looking at lights in the sky. You're participating in a cosmic conversation that began with the first moment of time, touching the edge of everything that was, is, and ever could be observed. You're standing at the edge of forever, and forever, in all its mystery and wonder, is looking back at you. How far can we see in the universe? We can see all the way back to the beginning of light itself. And perhaps, just perhaps, that's exactly as far as we were meant to see.